So what we are going to do now is we are going to take some application of this reciprocal space knowledge and see that how we can use this to characterize things like thin films and single crystals. So for a diffractometer, basically we can first define the diffractometer geometry and components. So this is, for example, sample stage. Typically within the sample stage you have x and y axis, and the z axis is, or z axis is the axis along which, or sort of little deviated, is the beam. So this is the perpendicular z axis, and beam somewhere comes at some angle to the sample stage. And this is true for a goniometer whose sample stage is perpendicular. So most of my reference point is the diffractometer, which is a typical thin film diffractometer, MRD Pro of Pananalytical. In that, basically what is there is, so if this is your sample stage is typically vertical, okay, and this is the beam that hits, and somewhere along this direction you have detector. So if you now put that into a circular form or a plate shaped form, so this is your sample stage, which is vertical. If you so the axis which coincides with the surface of this plate is the goniometer axis. This is the stage normal, and this is this is not the goniometer axis. Goniometer axis is the axis which is, so you have complete cradle, perpendicular to that is the goniometer axis. This line lies within the sample plane, and the angle which is made by the X-ray beam and the sample plane is the omega angle. The angle which is made between the transmitted beam and the diffracted beam is 2 theta. Sample rotation within its own plane is characterized by angle phi, and if you have, so this is your sample, if you rotate it in this fashion, this is angle psi. So you can see this is psi rotation, this is phi rotation. So if I take a, do I have a plate here? Yeah, I have a plate here. So this is the sample holder. So this is phi, okay, and if I do like this, this is psi, okay, and if this is sample, this is X-ray beam, then this angle is omega, and if this is X-ray, this is transmitted beam somewhere on the other side, this is diffracted beam, and the angle between those two is 2 theta. So you can see by geometry 2 theta and omega are coplanar angles, okay. So because this axis and this incident beam and transmitted beam, they are in same plane. So the key thing about reciprocal is
phi is about the stage normal.
Phi is about the stage normal, yeah, and psi is.
What are the axes? If you identify the axes, it will be easier.
So here, in general, you're not talking about the. You're just talking about mainly.
Psi का axis कौन सा है? Rotation है.
This psi. Psi is.
No, that is for phi. Phi for phi.
This is the stage normal. Psi is the angle which is. So if this is.
About which axis?
This is okay. Let me come to that. This is one line that is passing through the sample stage. If you draw another line that is perpendicular to the sample stage, if you rotate around that, that is psi. So if this is your plate, so if I say this is my plate here, I will rotate, this is phi, okay, around this, and around this axis if I do psi, I can do around this axis, I can do around this axis. So either of them will be psi depending upon how you want to rotate the sample, because now there are in some diffractometers, if this is sample stage, in some of them it is like this, and if it's a vertical diffractometer, it is like this. If it's a horizontal diffractometer, it is like this. So it's always along a line within the sample plane, you rotate it in such a fashion so that you are able to capture asymmetric planes. You see, the problem with 2 theta geometry is, let me now draw it on the board, okay. Now if you look at this sample, The problem with 2 theta geometry is this is your X-ray beam incoming, this is your diffracted beam, and most of the measurements that we do are in the reflection mode, they are not in the transmission mode. Now, for this to happen, your planes have to be parallel to the surface of the sample. Okay. Now, if you want to diffract from the planes which are at some other angle, you can rotate the sample around this axis and rotate it like this. So, this is the sample axis and you rotate in this direction. This is typically your psi axis of rotation for the sample, typically in the most diffractometers. So, if you rotate along this axis, it is phi rotation. If you rotate along this axis, it is psi rotation, and omega is basically this. Omega and 2 theta are these. So, this is 2 theta and this is omega. Typically in most diffractometers, because of sample alignment problem, omega and 2 theta are decoupled. For a Bragg condition to satisfy, omega is equal to theta, but omega is not equal to theta in most conditions because alignment is not perfect. So, in diffractometer language, you do not call it theta, you call it omega, because you can independently align it, you can independently move it to move the sample to align it. So, sample about its own axis is psi. So, around this axis it is rotating psi, along the normal it is phi, and within the plane of beam it is omega and 2 theta. So, on this side you have X-ray source incident optics, on this side you have detector and diffracted beam optics. Now, now what you have here in, now let us get back to reciprocal space back again. So, this is the origin of reciprocal lattice, this is your incident beam, this is your diffracted beam, and this is your reciprocal lattice vector, which we call as Q now. In most reciprocal, see, okay, for the theory purposes we describe reciprocal lattice vector as G, but when it comes to drawing the reciprocal lattice maps and drawing the axes, we define it as Q, not as G. However, G and Q are equivalent, they are not different to each other. So, so we can say that this Q, the trigonometric relation is, this Q is nothing but 2 sin theta into k naught, where k naught is nothing but 1 over lambda, which is the wave vector. So, for a Bragg condition, you can see that this for a Bragg diffraction to occur, your instrument probe should scan the point in such a fashion so that your reciprocal lattice coincides with the diffracted beam vector. Okay. So, that your diffracted beam is in such a position so that you are able to complete this parallelogram or this triangle. So, the instrument probe should coincide with the reciprocal lattice spot, and basically you can see from this line, if for a perfect lattice, not a problem, for a perfect lattice this angle and this angle are equal and you will get a perfect diffraction condition for an appropriate theta. However, imagine your sample is not perfect single crystal, your sample has some mosaic texture. You understand by mosaic texture, which means a single crystal would mean that this plane is 1 0 0 all throughout, and the 1 0 0 vector is also the same all throughout. If I measure from this point to that point all the way along the sample, this will always be 1 0 0 and this will always be 0 0 1. Whereas for a mosaic texture, you can have plane as 0 0 1, but for some grains 1 0 0 will be in this direction, for some other grains the 1 0 0 will be in this direction. So, it is like if you look at the floor, mosaic floor. So, mosaic floor will have all the grains aligned at certain angle with respect to each other. So, what will happen is that if I come to the other side, so if I look at the sample from top, okay, and let us say I divide sample in various sections, all of them are same plane 0, 0, 1. They are all 0, 0, 1 plane, but 0, 0, 1 plane has certain direction which is coincident. Let us say this direction is 1, 0, 0. So, for this grain 1, 0, 0 is in this direction, for this grain 1, 0, 0 is in this direction, for this grain it could be in this direction, for another grain it could be in this direction, and for this grain it could be again in some other direction. So, for a mosaic texture, the plane from top looks the same, but the planes are misaligned with respect to each other within the plane, okay, within the sample. If it was a single crystal, all these 1, 0, 0 vector will be along the same direction. Okay. There will be no discontinuity between various sections of the crystal. So, this is the difference between mosaic texture and single crystal. The reality with thin films is somewhere in between. So, what will happen in thin films is you will have strain, you will have dislocations at the interface, which allows you to have little bit of misorientation within plane as well as out of plane. If you have that, what are you going to have in terms of microscopically looking at the sample? A perfect single crystal will have perfect D spacing. Okay? A perfect D spacing will mean perfect theta. A perfect D spacing will also mean perfect G vector, well defined G vector. If you do not have perfect D spacing, what will you mean? What will it mean? You will have different G's, which means you will have multiple diffraction spots. So, what will happen is that, suppose this is the origin of reciprocal lattice, this is your perfect G vector, but in reality what will happen is you will have multiple G's around it. In order to capture these multiple G's because of variations in the D locally, you will need to vary this angle in such a fashion so that you are able to capture all of them. And this is what is the essence of reciprocal space mapping, to focus only on one particular diffraction spot, not all of them. See, in powder diffraction pattern you carry out all the, you collect all the spots simultaneously. Here the trick is to collect one particular spot and just fiddle around it, vary the angle little bit, just move around it, change your reciprocal lattice vector by little bit, so that you are able to capture all the misalignments and you are able to look at the smearing, which will allow you to calculate the D values precisely, and this will allow you to calculate things like strain as well as composition dependence. And because you know that by changing the composition you change the lattice parameters, by changing the strain you change the lattice parameter as well as the D spacing.
So, their origin should not be
sorry?
Origin must change in that case.
So, this origin is same.
Mosaic case.
Well, I mean, yes, you are right, but for the sake of analysis what you do is that this point also has to correspond to some point in the goniometer. Okay? So, let us say you fix it with respect to some point in the sample, that point we will have to fix.
So, each time the origin changes?
No, origin does not change, you fix the point in the sample. Sample.
With respect to the sample. But there, yes, the
So, what you do is that you fix the origin and you change these points. You take care of differences in these points and this point. So, all the misalignment here is translated into the misalignment at that point. So, what you have here is basically this k naught is nothing but 1 over lambda, and this d star, which is the reciprocal lattice vector length, is nothing but q, and this is 2 sin theta k naught, and of course, this is nothing but equivalent to the Bragg's law. So, now another key thing is the alignment of the sample. Remember, you can rotate the sample phi along some axis within the plane. So, this is the sample rotation in the phi axis, this is the psi rotation along some axis, and these are the coplanar angles 2 theta and omega. The key thing about reciprocal space mapping is now the reciprocal lattice point must lie within this plane consisting of the incident beam and the diffracted beam. So, the problem lies in, suppose your sample, the peak that you want to investigate, remember there are difficult samples which don't have diffraction spots in large numbers. Many samples give you diffraction spots only in small numbers, and the situation is complicated by the fact that you are looking at the reflection mode. So on one hand you are limited by the radius of evolved sphere, which is the limiting sphere. On the other hand, you are also limited by the geometry, because you cannot collect the reflections which are at higher or lower angles. As a result, the number of spots to inquire within the evolved sphere are very small in number. So not only the number of spots are smaller, because of this restriction, your systematic absences may make it worse. So you don't have too many points to investigate. So what happens is that, suppose you want to investigate this particular point. If this point doesn't lie within the plane of incoming and outgoing beam and the sample axis, then you won't be able to investigate it. So first thing is to make sure, if you want to investigate this particular point or array of points, they lie within the same plane. So what you do is that you rotate your sample by providing a phi rotation, and you basically what you do is that you look at a particular peak, set your detector at a particular 2 theta value, and rotate the sample. When you rotate the sample at some theta position, that particular peak will start diffracting if it lies within the plane. So after you have provided some phi rotation, that particular plane, which consists of the spot that you want to investigate, they all come within this plane, so that you are able to, so this is your origin of, so this origin is always fixed. So because the sample is fixed with respect to goniometer, the origin of reciprocal space is fixed with respect to that point. As a result, you choose a particular reflection point, and then you can always explore that point by changing these values of 2 theta and omega by tiny margins. So basically what you do is that before performing a scattering experiment, you change the azimuth. So basically, before a scattering measurement is performed, the azimuth containing the reciprocal lattice points of interest must be located in the same plane as the incident and the scattered beam. So this particular point must come within this particular plane, and this requires you to do some initial alignment of the diffractometer and the sample. So that is the first thing. So let us say we take gallium nitride sample. Gallium nitride is a very well explored material for these purposes, because gallium nitride makes very nice epitaxial thin films. And if you take a sapphire, gallium nitride is deposited on sapphire sample. Sapphire is alumina, okay, and it's a single crystal alumina. On that you deposit a thin film of gallium nitride. And if you look at the gallium nitride reciprocal lattice points in space, what you see is that the largest density of reciprocal lattice points is available only for two sections. The first section is 001 and 11 bar 20 section, and the second section is 001 and 10 bar 10 section. For other sections, other oblique sections, the reciprocal lattice point density is not very large, and that you can imagine. Suppose you have a crystal, there will be certain sections along which you will have lot of diffraction spots. There will be other sections which are oblique sections along which you will not get any diffraction points, not many diffraction points. So these according to lattice parameters, etc., and crystal symmetry, they give you, these are the two sections which give you largest number of lattice points. Hence you have a freedom to choose many more points to do the analysis. So let's say we first draw this reciprocal lattice space. This is the direction 11 bar 20, this is the direction 001 direction, and since it's in reciprocal space, you write this qx vector, this is qz, and this is qy, and this is qz. So along qy qz plane and qx qz plane, you choose either of them. Now now I was talking about the accessible reflections. So if you draw the reciprocal map of a given crystal, on that you superimpose the evolved sphere. Okay. Now this is the evolved sphere which I have superimposed, only the top half of the evolved sphere. The top part is limited by the maximum diffractometer angle, which in most cases is about 160, 170 degrees. most diffractometers do not go beyond 150 degrees. So, this is typically 150, 160 degrees corresponding to that. The lower side is because you are collecting in the reflection geometry, you have two regions which are inaccessible. The first region is the region for which omega is smaller than 0, because then you will go in the transmission mode, or 2 theta is less than omega. These are the two regions which are prohibited by geometry of diffractometer. One is the diffractometer angle, second is the transmission mode reflection. So, what you are limited is only this region, the region between these two small semicircles and the big semicircle. So, number of points that you can explore in reciprocal space are limited in number. So, for example, if you want to look at this particular spot, you have a wavelength coming, you have incident radiation coming in this direction, and you must have your direction in such a manner so that you are able to make this particular spot fall on one particular evolved sphere of this radius. Okay. If you are in this, if suppose you wanted to explore this point, you won't be able to access it because it is outside the geometry of diffractometer. So, any point that you want to explore must lie within these 3 semicircles. Yeah, it's the same thing basically in a little bit more bigger fashion. So, for FCC lattice, for example, for silicon with atoms at 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4, the only spots that are permitted are these spots, the ones in the blue. Anything else does not diffract, and so you can see that for this particular orientation, when your crystal orientation is such that this is your x axis, which is 110 direction, this is 001 direction, you only have handful of spots to look at. So, your beam orientation has to be with respect to diffraction achieved for these spots, ensuring that evolved sphere radius is smaller than the radius of this greater circle. So, for gallium nitride, this is one possibility. These are the spots typically chosen for diffraction. Now, I will get back to that a little later. So, this is the principle of basically aligning the sample and how many spots can you choose. Now, why is it important is the tasks that you can do are to measure the layer thickness, to measure chemical composition. You can also do mismatch and relaxation at the interface, because mismatch and relaxation provides changes the strain in these materials, especially in thin film forms. You can measure the lattice parameters accurately. If you do complex analysis, you can also measure the defects in crystal size as well as the lateral structure of materials. So, you can do all of that. In this lecture, we will mainly limit ourselves to the measurement of de-spacing, which is related to these 3 aspects: chemical composition, mismatch and relaxation, and lattice parameters. So, let us say you have thin films like this, you have silicon with silicon germanium or silicon with silicon carbide, depending upon the mismatch between the lattice parameters. So, you have a substrate, okay? The substrate is single crystal. On that you deposit a thin film, let us say 10 nanometer, 20 nanometer thin film of silicon germanium or silicon carbon. Depending upon the ratio of silicon germanium silicon carbon, your lattice parameter will change. So, the lattice mismatch is delta A divided by A reference, which is basically the substrate. So, change in the lattice parameter of film or layer minus the substrate divided by lattice parameter of substrate will give you the thin film strain. So, for a compressive strain, typically this delta A divided by A substrate is greater than 0, and for tensile strain, delta A divided by A substrate is less than equal to 0. So, this is a typical notation that is taken. You can see that depending upon the value of this strain, what will happen if this strain is too large?
Probably there is a debonding.
You have a debonding, very good. And what is that debonding going to lead to?
Fall of
No, you will not have peeling off in many cases. You will have dislocations, right? You are trying to match atom to atom, but atom to atom matching requires that bond should stretch, since substrate is thicker and rigid, the bonds in the substrate do not stretch, it is the bond in the thin film which stretches or compresses. So, the thin film will be strained either in tensile or compressive fashion, but if the compressive or tensile strain is too large, then let us say if you want to match 10 nanometer by 10 nanometer or 10 angstrom by 10 angstrom, you will have 10 atoms at the bottom, you will have 11 atoms on the top. What will it mean? That one atom is free, and this free one atom will mean a dislocation. So, you will create dislocations in the interface. The moment you create dislocations at the interface, you call it a relaxed interface, which means the strain has reduced in the thin film. If you do not have any dislocations, the thin film will be strained as far as possible, it will be a strained thin film. So, this is what we can examine, whether how much is the strain in these thin films by looking at the reciprocal lattice spot position.
I have a small question.
Yeah.
You talked about like the strain being the origin for having, these are called as threading dislocations, right?
These could be threading dislocations, yeah.
I was wondering, like if one were to look at the stress values, is
Yeah.
it like the theoretical strength, like for, because you can always calculate theoretical stress that is required to nucleate a dislocation.
You can always calculate that, but see the thing is in the 2D media, see this is typically a 2D media. This is not a you are looking at a substrate whose thickness is about half a millimeter or 1 millimeter, and a thin film whose thickness is 100 nanometer. So, a thin film is essentially a 2D media, it is not a 1D media. So, situation is very different from the bulk. If you look at now these two pseudomorphic layers, pseudomorphic means the two materials on top and bottom have similar structure. If you look at these, so for the pseudomorphic layers, you will have certain points matching in certain direction. So, you can see that if you look at these two layers, you have lattice matching in this direction, but the film is allowed to relax in this particular direction. So, if you look at the reciprocal lattice point space, the purple ones are substrate spots and the pink ones are the fully strained layer. Since there is complete alignment in this direction, the lattice points, what do you expect the overlap between these 2 points? You expect these 2 points to overlap along those directions. So, you can see that if you go along 100 direction, in this case these are the 100 directions, you can see that substrate and thin film points, they overlap with each other. But the moment you go along this direction, which is the 001 direction, you can see that these points now start shifting with respect to each other, because that is where you have difference in the plane spacing. Correspondingly, you can draw the 2D map where all of these points will be located in the 2D space, and you can see for asymmetric points, you will have some gap between the 2 points. So, if you are able to draw these 2D maps theoretically, what this tells you theoretically? It tells you first what is the strain level by measuring the spacing between the 2 points, and by measuring the exact location of 2 points, you can calculate the exact D spacing and the changes in D spacing. But you will have to do that not only for the symmetric spots, but also for the asymmetric spots to get a complete picture, to get different strain contributions to the sample to create a complete picture. Completely relaxed layer will give you slightly different. You can see that if you have a layer which is relaxed, which means the lattice parameters are slightly different here, which means the atom to atom correspondence is not maintained in the layer anymore. As a result, the in plane lattice parameters are different, and you can see that along this direction also you have some change in the spacing. So, you can see that this asymmetry starts coming in the asymmetric reflections, where they start spreading out diagonally instead of going in vertical direction. In the previous slide, they were spreading only in vertical direction, but here not only there is a mismatch in this direction, there is a mismatch in this direction too, and you can see that there is a mismatch in the diagonal direction as well. So, the reason why I am giving this information is because when you examine thin films, you must know what you are investigating and what kind of profile you expect for a given sample. So, basically what we are going to do here is, so here this is the Q vector for a given sample, this is the incoming beam, this is the outgoing beam, and if you investigate in such a manner so that your Q is always in this direction, this is called as a symmetric scan, and also maintaining that omega is always equal to 2 theta divided by 2, which means omega is equal to 2 theta. This is called as a symmetric scan. In the asymmetric scan, what happens is that the beam is very nearly parallel to the substrate or the sample. In this case, the 2 theta angle for a given plane, let us say this particular plane, which is the incoming beam plane, is very large. The angle between the transmitted beam is very large. In this case, what you are investigating is not this plane, rather some plane at an angle for which the Bragg condition is satisfied. Remember, for this case you will always investigate the samples planes which are parallel, because for those planes this angle and this angle are equal. The moment you go to this geometry, you no longer satisfy the Bragg condition for the surface planes. You satisfy the Bragg condition for the planes which are inclined to a surface, and these are this kind of a scan is called as a asymmetric scan. I will come to that a little bit more detail later on. So, so basically to get many more scans you need to fit many more peaks which lie within this reciprocal space. So, for example, for this particular sample you have only 5 choices of peaks, and you can only investigate these 5 peaks. So, this is for instance a picture of this is a you can see that this is one scan of a particular Q vector at a given location in this space, and you get multiple peaks here. This does not give you much information, but if you take multiple scans, so this you can see that this is one crystallographic direction, this is along another crystallographic direction. So, this one scan is taken at one, so you vary the Q vector in one particular direction while maintaining the Q vector of other direction fixed. So, you collect one scan, this we will define as 2 theta omega scan later on, and then you successively collect many scans and plot them in such a fashion so that you are able to plot the intensity as a contour while providing the vectors on both the directions. I will come to that a little later, perhaps it is not very appropriate here. So, what you do in this case is you have 2 kind of methodologies. First is the double axis measurement, where you rotate the sample and you move you rotate the sample around its own axis, and then you rotate the sample along this axis, which is the omega axis. This is typically called as a double axis measurement. In the triple axis measurement, what happens is that you also rotate the analyzer crystal through which the beams go to the detector. What this does is, if you directly take the beam from the sample to detector, then the aperture of the detector is limited. As a result, you are not able to collect a lot of data, which means you won't be able to collect huge variation in omega. If you put an analyzer crystal which can again rotate through certain angle, then you can have larger variation omega to get to the detector. So, you need to put an analyzer crystal to increase the omega range on this side to get you larger angular range. So, this triple axis basically it also removes height kind of errors, and it allows you to good profiles and scans. Anyway, I will come to that a little later. So, what basically, let me explain you again. What you are going to expect is, if you have tilt and mosaic in the sample, which means suppose your planes were parallel to each other, okay? Suppose your planes were parallel to each other, then if they were parallel to each other, then you will have shift. If you look at the reciprocal lattice points, look at the right picture first, okay? If you look at the right picture first, if this is the origin of reciprocal lattice 0 0 0, and the d spacing of these planes is different to d spacing of these planes, right. So, the reciprocal lattice vector of these greens is going to come at a higher height. So, if the reciprocal lattice vector spot for, this is for films, the substrate has lower d spacing, as a result it will be even farther. This will be for the substrate. Okay, is that clear to everyone? Because the d for the substrate is lower, as a result g will be larger, because this is 1 over d. Now imagine a situation, if your substrates, if your thin film has variation in the d spacing along this direction, what do you expect? You will have variations in the d. Variations in the d will give you elongation of this spot. So, what you see in the data is the elongation of these particular multiple g values occurring around the spot in a particular direction. So, this will give you elongation. So, if you have variation in the d spacing, you will get a variation in the length of this spot. However, when you have variation in the d spacing, apart from having a tilt, which means the planes of the films are tilted by some angle to the planes of the substrate, then not only you will get a shift in this direction, you will also get a lateral shift, because the crystallographic vectors are now misaligned. As a result, you will have little misalignment between the spots in the reciprocal space. So, and if you have this kind of misalignment, where you have multiple misalignments, let us say a mosaic texture, where your perpendicular vector has sort of little bit randomness associated with it, in that case it also leads to changes within the q vector as well. So, not only you have a smear in this direction, but also a smear in the other direction. So, effectively what you are going to examine in these reciprocal space maps is the profile of these spots, whether they elongate or whether they spread in x axis or whether both. So, that is what we are going to examine. So, this is for example one example of spot. You can see that this is for epitaxial layer of nickel antimony on some substrate, and you can see that there is a strong elongation in one particular direction, and this is along the x axis, and this tells you that you have a lot of mosaic texture in the thin films, and this is very common in metals. I will come to that a little later, and you can determine C lattice parameter. So, let us say what are the scanning options. There are various different possibilities for exploring this diffraction space. So, you can change, you can either scan the instrument or you can scan the sample, and you can do this by adopting multiple strategies. For example, you can employ a little bit change in 2 theta, let us say we define it as delta 2 theta, or we employ a change in omega whose change which is depicted by this delta omega. This will, the moment you change theta and omega, remember in the reciprocal space you will also change the q vector, and you are basically looking at the change in the q vector by employing these changes, which is nothing but delta q. So, so for instance, you have this perfect picture here, you have a particular omega for which you have a particular 2 theta, and this is the q vector for a very specific q spot. What you do here is basically you rotate this omega in such a fashion so that you have tiny variation of omega, resulting in tiny variation in 2 theta, which gives you tiny variation in the q spot. Now, this is a symmetric scan, meaning that there is tiny, so the variation in delta omega or delta theta results in variation in the q vector, which is delta q. So, what you are recording basically is a 2 theta omega coupled scan, where you measure the intensity, changes in the intensity with slight variation in the 2 theta omega. If it was a perfect crystal, what would you expect? If it was a perfect crystal, what do you expect? You will expect a single line, right? But since crystals are not perfect, they have strains, they have various other defects with them. Yes, Anand.
These are thin films, right? So that at least one of those examples where you were doing.
Thin films will also lead to that.
You were telling that there is actually a lattice, you are filtering out that part, or?
No, so what you can do, basically the let me just. So if you look at the, so you have Qx and Qy space, and if you look at one particular spot which is assumed to be a point, you will have variation in this direction, variation in this direction, right? So from an ideal picture perspective, you will have, this will correspond to the changes along, let's say, the perpendicular direction of the sample, which is along the film normal. This will correspond to the axis which is in plane axis of the thin film. What you are saying is also true in thin films. In thin film, since thin film carry two kinds of stresses. One is the internal stresses, second is the intrinsic stresses. So what is tricky here is to work out the to deconvolute both the parts, the intrinsic contribution and the extrinsic contribution. For that, what you do is that you deposit thin films of various thicknesses and then empirically do that exercise. So if you have variations, if you have let's say variations in the d spacing of the sample or variations in the crystal texture in the sample, you will have some variation in the intensity of this 2 theta along a particular value, and the broadness of this peak will determine the limit of non-ideality in the structure of the thin film. You can plot this measurement either as intensity versus 2 theta / omega, or you can convert these angular units into the reciprocal lattice units. So this intensity can also be plotted as Q. Typically, the convention is to plot intensity versus Q rather than intensity versus 2 theta because this gives you better data representation and ease of calculations. So, the shape and size of the profile that you measure, the shape and size of that profile is basically dependent upon the shape and size of both reciprocal lattice spot, which means the variations within the sample, but also along the also on the instrument, because remember the X-ray beam itself which is coming on the sample, that also has inhomogeneities associated with it. Okay, it could be because of monochromatic crystal, it could be because of the beam spread, lot of other things. So it is often important to use very good optics of the X-ray when you want to analyze this kind of data, so that you minimize the extraneous contribution of the instrument than the sample. As a result, it's very important to use high quality monochromators and high quality analyzers, so that you minimize this instrument probe size and shape effect. So scan units, basically I was talking about, you can plot the data as intensity versus 2 theta or intensity versus Q. There is a relation between these two. Let's say this is reciprocal space Qx and Qz axis, and this is the particular diffraction point you want to explore. This is the incoming beam, this is the diffracted beam, and if you just so this is the angle between the Qx direction and incoming beam, which is omega, and the 2 theta is the angle between the incoming beam and the transmitted diffracted beam, which is 2 theta. And if you now look at the geometry, you can define various angles in different ways, and you can write a geometrical relation between the angular position and the different space coordinate. So what you will find is this Qx, which is the which correspond to some theta and omega value, can be written as r cos omega minus cos 2 theta minus omega, and Qz, which is in this direction, can be written as r sin theta plus sin 2 theta minus omega, fairly symmetric expressions because of symmetry of reciprocal space, and R is nothing but 1 over lambda, which is either basically mod of k. All right. So, now let us look at what are the symmetric versus asymmetric scans. So, if you look at this sample, which is typically 001 oriented, which means that the 001 type of planes are parallel to the surface. So, a symmetric scan would mean that you are only exploring the planes which are parallel to the surface, which will ensure that this omega is equal to theta, or 2 theta by 2 is equal to omega. So, this information gives for C axis oriented thin films the information regarding the C lattice parameter, which is in this direction. So, you do two types of scan for that, either the omega scan or the omega 2 theta scan, which I will come to in a little while. The asymmetric scan is scan which is not for the planes parallel to surface. It could be 102 plane, it could be 104 plane, it could be 114 plane, and they are basically useful in generating a complete reciprocal map rather than looking at only one point along the QZ axis. So, if you want to make if you want to get the plots somewhere here, you need to make a asymmetric scan of some of the peaks, which means you need to take the beam nearly parallel to the surface, and this would be the direction of detector, and then you are looking at a plane which is at some angle to the surface. So, a 2 theta omega scan typically is, it is called as a radial scan. The step size here, which is delta 2 theta, it has twice the value of change in incident beam angle omega, which means delta 2 theta is equal to 2 times delta omega. And basically what it means is that the moment you do that, which means you change this by delta omega, correspondingly this changes by delta 2 omega 2 theta, and this diffraction vector in that case remains symmetric, which means it remains perpendicular to the plane of the substrate, except that its length keep changing as you change the magnitude of omega. So, this is called as 2 theta omega coupled scan, where this condition has to be followed, delta 2 theta is equal to 2 delta omega. Another scan is called as 2 theta omega scan, which is a special case, same as before, except that when theta corresponds to theta Bragg, which means you are basically looking at the planes which are dead parallel to the surface, which means there is no asymmetry in the sample at all. So, this is the ideal case where theta is equal to omega. In most cases, theta is not equal to omega because sample planes are never parallel to the surface, they are at certain angle to the surface. As a result, theta and omega are not the same. Theta and omega are same only for perfect Bragg condition, which is for perfect planes. Hang on, what did I do here? So, these are typical 2 theta scans, 2 theta omega scans. This is for example for gallium nitride, aluminum gallium nitride multilayers. One key requirement is that the peaks of the sample and the substrate must lie close to each other, so that there is epitaxial arrangement between the two. And that will also ensure that planes are parallel to each other. So, for instance, here you have used sapphire wafer, but the layers are gallium nitride and aluminum gallium nitride. If you look at the overall scan, it appears as if these two peaks overlap with each other. They only shift with respect to each other as you go to higher angles. But if you do a 2 theta omega scan with very small step sizes with high resolution optics, you will be able to resolve these two peaks within a fairly good range. So, for example, if you make a measurement from 34.5 to 36 degrees within a 2 theta range of 1.5 degree, you will be able to separate out gallium nitride peak and aluminum gallium nitride peak by doing this 2 theta omega measurement, because since both the layers are on top of each other, they are strained. There is some changes in the d spacing of both the layers because they have changes in the lattice parameters, and you will be able to resolve the peaks. However, what it requires is that if you look at these two peaks, the separation between these two peaks is about half a degree, okay, which means the instrumental resolution has to be greater than that. Secondly, if you look at the peak width of these two peaks is 0.08 degree and 0.0901, almost 0.1 degree. Your step size has to be smaller than that. Your step size cannot be the peak width itself, otherwise you will observe a hump kind of thing. Yes?
What about this normal 2 theta scan? It's not a 2 theta omega scan.
2 theta omega scan is also represented as 2 theta scan sometimes.
Oh, this is not, it's a special, it's not the same as the law.
Sorry, no, this is the overall 2 theta scan, and this is performed using 2 theta omega scan to resolve the two peaks. Sorry? In this one? Okay, because I mean here 002 peak will be somewhere here, and it's just merged with the 002 peak of aluminum gallium nitride. It could be because the thin film thicknesses are different. It's in this fashion because gallium nitride 002 is for the film which is much thinner than aluminum gallium nitride thin film. So this is a thicker film, this is the thinner film. That is why you have a separation in the intensity. But if you don't do a 2 theta omega measurement, you only see a single peak. You don't see the two peaks. And you can also do offset scans, which is for asymmetric scan. In these cases, omega is not equal to theta. As a result, when you have the difference between the two values is called as offset O, and as a result, since you are now looking at a plane which is asymmetric plane, which is not parallel to the surface, your Q vector is also in some other direction. So this is your offset scan where your theta and omega do not match with each other, because remember, omega is the angle between the surface and the incoming beam, whereas theta is the angle between the plane of diffraction and the incoming beam. If there is a large difference between theta and omega, then you are looking at a plane which is asymmetric. So this kind of scan is asymmetric scan, offset scan. So this will ensure that your Q vector doesn't lie in the direction perpendicular to the substrate, rather it lies in a direction which is at certain angle to the substrate in the reciprocal space. So basically reciprocal space mapping is about scanning along these two methods. What basically you want to do is that so the way you carry out is you fix first 2 theta, carry out one 2 theta omega scan, carry out another 2 theta, carry out another 2 theta omega scan, or carry out, so you take multiple scans at various 2 theta values. So you will have a grid of measurements. What you will have is so let's say this was your 2 theta. You know that this is where your ideal 2 theta should be, 2 theta B. So the idea is to carry out many omega 2 theta scans around this 2 theta value. So you carry out multiple scans on this side, multiple scans on this side, and generate a complete map for various values of 2 theta and omega. And if you convert those 2 theta and omega values into reciprocal space, you will create a reciprocal space map, because 2 theta and omega values are related to reciprocal lattice units. Remember, this exercise is valid only for samples which are single crystals or nearly single crystals. It is not valid for polycrystalline specimens. So basically a 2 theta, a 2-axis reciprocal space map can be obtained when you repeat 2 theta omega scans for a sequence of offset values. Okay? So many offset values are chosen. So if you look at the previous exercise, this is one offset value. You take many omega values, which will give you different offset values. So the difference from one offset value to the next is called as delta O, which is the omega step size. And the total difference between the largest and the smallest offset is the omega range. Okay? So you have a fixed omega. So you have ideal omega. What is ideal omega? Theta B. So basically across theta b you choose various offsets, and those offsets will give you different. So this is theta b, you go on this side, you go on this side, 1 degree on this side, 1 degree on other side. This will give you complete map of omega. So complete information about misorientation of a particular plane in the crystal. But this exercise doesn't need to be, it needs to be carried out not only for one peak, you need to carry out for multiple number of peaks to get exact information about a sample, and it's very precise. So now let's look at rocking curve. A rocking curve is slightly different. It's nothing but what we are talking here, except that here the source is fixed, the detector is fixed, but the sample is rocked around the Bragg peak slightly. So here what you have here in this case is, this is your incoming beam, this is your diffracted beam, and you rotate the sample around this axis in this fashion. So what will happen when you rotate the sample around this fashion? Since your omega is fixed, what are you expecting? What do you expect here will happen? You will have multiple beams coming out in multiple directions of 2 theta. Some beams will come out at 2 theta 1, some will come out at 2 theta 2, around that value of 2 theta, which is a fixed value. So if you have planes which are not perfectly parallel to the surface, rather in some sort of zigzag fashion at the surface, you will be able to capture all those planes which are at certain angles. So let's say you have a thin film like this. So in an ideal case, you will have thin film which will have planes going like this. But in a non-ideal case, you will have thin film where you will have planes with various angles on the surface. And if you rock this sample, you will be able to capture all those planes which are inclined to the surface by a tiny degree. Remember, it is not for the planes which are perpendicular to the substrate or very large angle. It is only for a very tiny variation in the misalignment, maybe about 0.1, 0.2 or 0.5 degrees, not more than 1 degree certainly. So, so when you do that, you measure the variation in the 2 theta values, and what you plot is basically intensity versus omega scan, and broader this scan is, what does it mean? The sample is more misaligned. It has poorer crystalline quality as compared to something which has a sharp line. So if it was a perfect single crystal, you should get a straight line. The broader the line is, the more non-uniformity in the sample is. So basically, when you measure the full width half maxima of a rocking curve, this is an indication of crystalline quality of the sample. So this is the first test generally you can do on single crystals to perform the rocking curve before you generate the complete reciprocal space map. So omega 2 theta scan will give you completely different picture, because omega theta scan is 2 theta, because you're looking at much more finer picture by coupling both of them. But if you perform only omega scan, you will get a broad hump only around a particular peak. So in the reciprocal space map, what it measures is, let me come back to next one. Yeah. So in the reciprocal space map, what it measures is, this is the reciprocal space map in qx and qz direction. This is the this particular plot makes a plot of omega offset versus 2 theta omega, which can be translated into qz and qx by making the transformation of axis. If you choose a particular horizontal line which is at constant offset, which means at constant offset del theta minus omega, I can make a plot of intensity versus 2 theta omega. So you vary this axis, which is 2 theta omega, or you measure 2 theta as we conventionally call it, plot the intensity at a constant offset. So you will basically, this map is nothing but putting together multiple maps 2 theta omega taken at various theta minus omega values, okay, for a given peak. Sharper these peaks are, sharper the smearing is, lesser the smearing is, sharper the peaks are, which means better the quality of thin film is and more strained it is, and broader it is, you are expected to have more poorer crystalline quality. Also what it does is, by looking at the relative position of these spots with respect to each other, remember this is a reciprocal space. Since it is a reciprocal space, it is, each point is associated to a vector. If they are aligned in one particular direction, which means they are aligned, there is alignment along one particular direction. However, if these 2 points, one point lies here, another point lies here, by measuring the angle with respect to the origin, you can determine what is the misorientation between the sample and the film. So not only you can calculate the D precisely, you can also calculate the misorientation between the two spots precisely. So this will give you information about strains, about the orientation relationship, about the composition effect, if you measure the D values precisely. So these are, for example, some samples. Here, tell me which sample is good here. The first sample is good because you can see that spots are much more well defined. Secondly, the alignment between the spots is good. So if the spots lie along this vertical line, which means they are strained, if they move away from each other, this is the relaxed line, which means if they were completely relaxed, this spot would have moved here. Okay? So you can see that as you increase the thickness of the film from 50 to 65 to some other composition here, you can see that this spot gradually starts moving to the relaxed line. What it tells you is that thin films are getting more and more relaxed as you change the thickness of composition. And by measuring the D spacing precisely, you can calculate the strain values and any composition effect. Substrate is gallium nitride, yeah. Because remember, it's taking the see, X-ray also doesn't penetrate deep into the sample. You can, in these scans, you choose your measurement conditions, such a situation, so that your penetration depth is not very large, especially if you are looking at asymmetric peaks. Then beam is coming almost parallel to the substrate. So you are looking at the planes which are parallel to the interface. So at interface you have effects on the substrate as well, and there could be interfacial reactions and things like that. Oh no, in this case actually it's gallium nitride and aluminum gallium layers on sapphire substrate. I am sorry. So this is gallium nitride layer, and this is aluminum gallium nitride thin film on top. So these are two thin films. So in this case sapphire substrate is used. So basically you can use, you can measure the plane spacing from the reciprocal space maps by looking at by doing a detailed calculation of D spacing from the spots at various positions, and this can be used in strain calculations, estimating structural distortions, orientation relations, etc. So what's the time now? 5:05. Very good. So we have exhausted 3 hours only in reciprocal space. I have a few more slides on this, but I will not talk about them. You will be provided these slides where I have provided a few methods of calculating the D spacing, which you can read yourself, and there is nothing too significant about it. The purpose was to tell you that what exactly this method can do and how do you do the measurement. Any questions at this point? Huh? Any book is there? As I told you, there is no book. There is only one monograph by Paul Fuster. Paul Fuster, I provided that reference in the first slide. Paul Fuster, Reciprocal Space X-ray Scattering in Semiconductors, published by Imperial College Press. This is a very new area. The technique evolved only about 15-20 years ago, and it's still not used by many people because it's not easy to carry out. Also equipments are expensive, but it's a very good technique for understanding single crystals. Okay, so these are some slides on D spacing calculations. You can read it yourself, and so I'll leave it to yourself. Okay. So these are some references here. Paul Fuster's 2 papers, and then Peter Kidd, he has written this XRD of gallium nitride and related compounds. So these are 3 references, mainly from Pananalytical, and thank you.